Imagine this. You are looking up at a beautiful night sky. The stars are twinkling. Suddenly, a new star appears. It grows brighter and brighter. This is not a star, but a rock from space, hurtling towards our home. This idea has fascinated and frightened humanity for generations, shown in books and films. But this is not just a story. These rocks are real. We call them near-Earth asteroids, or NEAs, ancient travelers, silent wanderers of the cosmos. They sometimes cross paths with our small blue world. They hold secrets of the solar system's birth, but they also carry a potential threat we must understand. What exactly is a near-Earth asteroid? A rocky body whose journey brings it close to Earth's orbit. Scientists define a near-Earth object, or NEO, as any small body that passes within 1.3 astronomical units of the Sun. 1 astronomical unit is the distance between Earth and the Sun, about 150 million kilometers. NEAs are the asteroids in that group, not icy comets. Each one a story, each one a data point for safety. Their orbits are wonderfully diverse. Scientists sort them into 4 families. Aten asteroids, average orbit inside Earth's, but cross our path. Apollo asteroids, larger orbits than Earth, but cross us, the largest group. Amor asteroids, approach closely but stay outside Earth's orbit. Atera asteroids, orbit entirely inside Earth's path. Where do they begin? For most, far from us, in the main asteroid belt between Mars and Jupiter. For billions of years they orbited in relative peace. But the universe is dynamic. Jupiter's gravity can stir the belt. Collisions can send fragments flying. Disturbances can nudge asteroids out of stable orbits. Those nudges send them onto new paths into the inner solar system. And that, my friends, is how a simple asteroid becomes a near-Earth asteroid. So, we know where they come from. But what are these NEAs actually made of? Are they all the same? Not at all. They are as varied as the rocks on our own planet, perhaps even more so. Scientists classify them into several types based on composition. We learn this from the light they reflect. The most common are the C-type asteroids. C stands for carbonaceous, very dark ancient objects, carbon, clays, organic compounds, cosmic time capsules from 4.5 billion years ago. Then we have S-type asteroids. S means stony, brighter than the C-types, silicate rock, nickel, iron, a more processed, heated history. A third major group is M-type. M stands for metallic, remnants of metallic cores from shattered bodies, nickel, iron. But many asteroids are not solid single rocks, they are rubble piles. Close-up, detailed photograph of a rubble pile asteroid showing its loose gravelly surface, boulders, pebbles, dust, like cosmic sandcastles. Recent missions, Hayabusa 2, OSIRIS-REx, by landing on Ryugu Bennu and bringing back samples, they confirmed rubble pile nature. This discovery is crucial for science and planetary defense. Pushing a solid rock is very different from pushing a pile of gravel. Understanding their makeup is not academic, it's vital. Composition tells us density. Composition tells us strength. It tells us how they'd react on a collision course. Would it burn up harmlessly? Would it break into many smaller pieces? Or would it hold together and strike with immense force? Knowing what an asteroid is made of is a critical piece of the puzzle. It helps us choose the right strategy to defend our planet. It's the difference between knowing your opponent and facing an unknown enemy. This knowledge empowers us. Are these near-Earth asteroids truly a danger to us? Let's consider the facts calmly. The probability of a large asteroid, one that could cause a global catastrophe, striking Earth in our lifetime is extremely low. Very, very low. The sky is not falling. However, the risk is not zero. Even smaller objects, which are far more common, can cause significant damage if they enter our atmosphere over a populated area. We have seen proof of this in recent memory. It is a matter of when, not if, another impact will occur. Let me take you back to a cold morning in February 2013. In the skies over the Russian city of Chelyabinsk, An asteroid exploded. This rock was only about 20 meters across, the size of a 6-story building. It entered the atmosphere at incredible speed and detonated with the force of nearly 30 Hiroshima bombs. The blast created a powerful shockwave that shattered windows across the city. Over 1,500 people were injured by flying shards of broken glass. The Chelyabinsk event was a wake-up call. Even a relatively small, untracked object can have serious consequences. Scientists call the most concerning ones potentially hazardous asteroids, or PHAs. For an asteroid to be labeled a PHA, it must meet 2 conditions. First, its orbit must bring it very close to Earth, within 0.05 astronomical units. That is about 7.5 million kilometers, or roughly 20 times the distance to our Moon. Second, it must be larger than about 140 meters in diameter. An impact from something this size could devastate an entire region or small country. An object larger than 140 meters could create a crater several kilometers wide and cause catastrophic damage on a regional scale. An asteroid over 1 kilometer in diameter, though much rarer, would have global consequences. Its impact would throw so much dust and debris into the atmosphere that it could block out sunlight for months, leading to a collapse of agriculture and a worldwide impact winter. This is the kind of event that likely led to the extinction of the dinosaurs. Therefore, finding all the PHAs, especially the larger ones, is a top priority for the space agencies of the world. It is a cosmic search for needles in a haystack because our safety depends on it. So, faced with this cosmic reality, what is our plan? Do we simply wait and hope for the best? Absolutely not. Humanity is not a passive observer. We are taking action. The global community, led by space agencies like NASA, has developed a clear and methodical strategy. This is known as planetary defense. It is a serious, scientific endeavor with 5 distinct and logical steps. Each step builds upon the last, forming a complete chain of action, from discovery to response. This is our duty to ourselves and to future generations. The very first step is the most fundamental. Find. We cannot protect ourselves from a threat we do not know exists, so we search. Day and night, powerful telescopes on the ground and in space scan the heavens. Surveys like the Catalina Sky Survey and Pan-STARRS are our sentinels. They take pictures of the sky, and sophisticated software compares them to find the tiny points of light that are moving against the background of fixed stars. These are the asteroids. A new generation of more powerful telescopes will dramatically accelerate this search, like the upcoming NEAs Surveyor space telescope, helping us find the majority of hazardous asteroids much faster. Once an object is found, the second step begins. Track. A single discovery is not enough. We must follow the object. Astronomers around the world, both professional and amateur, take multiple observations over days, weeks, and months. Each new data point helps to refine our understanding of the asteroid's orbit. With enough tracking data, we can project its path far into the future with incredible precision. We can determine if, when, for decades or even centuries to come. This tracking is what turns an unknown threat into a known, predictable event, giving us our most valuable asset, time. The third step is to characterize. Once we are tracking an asteroid, we need to learn everything we can about it. What is its exact size? How fast is it spinning? What is its shape? And what is it made of? Is it a solid rock or a fragile rubble pile? We use various techniques, including radar observations from giant radio telescopes and spectroscopic analysis of its reflected light, to answer these questions. This detailed characterization is vital for the next step. Then comes step 4, deflect. If, and only if, we find an asteroid that poses a credible impact threat, we must have a tested and ready plan to change its course. And finally, step 5 is to mitigate. This involves international coordination and emergency planning to deal with the consequences if an impact cannot be avoided. So we come to the final, crucial question. If we find an asteroid on a collision course with Earth, what can we do? How do we deflect it? This is not science fiction. These are real technologies being developed and tested now. The leading and most proven method is called a kinetic impactor. The idea is wonderfully simple. Cosmic billiards. You send a high-speed robotic spacecraft to collide deliberately with the asteroid. Not to destroy it, but to give it a small, precise push. A tiny velocity change over a long journey adds up to a big shift in final position, missing Earth entirely. This is not just theory. It has been proven to work. In 2022, NASA flew the Double Asteroid Redirection Test, DART. It was a historic moment. The DART spacecraft, about the size of a vending machine, traveled millions of kilometers to intercept Dimorphos. It slammed into the asteroid at over 22,000 km/h. Telescopes on Earth and in space watched closely and confirmed the impact altered Dimorphos's orbit. For the first time, we moved a celestial object in a planned, measurable way. We proved we can change an asteroid's path. Another idea is the gravity tractor. No impact. Fly a heavy spacecraft alongside the asteroid for a long period, perhaps months or years. Like the Sun holding Earth, the spacecraft exerts a tiny gravitational pull. Over time, that gentle, persistent tug shifts the asteroid onto a safer path. It is slow, controlled, and highly precise, ideal with many years of warning. And then, there's the nuclear option from movies. The nuclear option. An absolute last resort, used only for very large asteroids with little warning. The goal wouldn't be to shatter the rock, which could create many hazardous fragments, but to vaporize part of its surface with a near-miss detonation. That creates a rocket-like thrust to change trajectory. Powerful, but risky, reserved for the gravest situations. We must continue our watch. The chance of a major impact in our lifetimes is small, but the consequences are too great to ignore. Through careful and continuous searching, tracking, and scientific study, we arm ourselves with knowledge. Knowledge gives us time, and time gives us options. By developing and testing deflection technologies, we're taking responsible steps to safeguard our planet. This is science at its most noble. It is not about fear. It is about foresight, preparation, and quiet confidence from understanding the universe and our place within it. We are the guardians of this beautiful blue marble, learning how to protect it.